Hello everyone. Today we would like to introduce Telecommunication Laboratory 1 Part 7. This part involves frequency modulation or FM. The frequency of the carrier signal will be varied. FM is classified into two types, that is narrowband FM and wideband FM. Okay, experiment 1. We will simulate narrowband FM. Narrowband FM may be called indirect generator of FM wave or Armstrong transmitter. Firstly, we put the phase shifter in the immunotherms. The buffer amplifier will also be used. Next, we put the multiplier in the immunotherms. For this experiment, we already construct the transmitter. Then, we use the adder module. After that, we use the message at the input of the phase shifter. Phase shifter and the buffer amplifier are used to construct the indicator. We will change the sine wave to cosine wave by using the indicator. Since the immunotherms don't have a 2 kHz cosine wave, next, we display the message signal on the oscilloscope. Okay, this is the sine wave that have a frequency of 2 kHz. Then we connect the output of the phase shifter to the input of the amplifier. Next, we show the output of the amplifier on the oscilloscope and also show the message signal. We will see the message like this. The output signal must be the negative cosine. Okay, we will observe the phase difference by adding the measurement as follows. Next, we adjust the phase difference to 90 degrees. It is observed that the blue wave is the negative cosine. We will review again how to add the measurement. Firstly, we place the measure button on the oscilloscope. Source 1 is channel 1 and source 2 is channel 2. Next, we click delay phase and select phase. After that, we connect the output of the amplifier to the input of the multiplier. Then we connect the sine wave that have a frequency of 100 kHz to the input of the multiplier. Typically, the FM signal is separated by Taylor series. Narrowband is the range of low frequency. In general, Taylor series is an infinity sum of terms. The first and the second of the sum term will be chosen for narrowband FM. Okay, we display the output of the multiplier on the oscilloscope. It is found that both signals have phase difference. Because the input of the multiplier is the cosine wave. The blue wave is not narrowband FM. Therefore, we connect the output of the multiplier in the input of the adder. Gain of the adder must be 1. We won't check the gain, but you should check it. After that, we connect the cosine signal to the input of the adder. Alright, this is the narrowband FM signal or transmitted signal or modulated signal. We display it on the oscilloscope. We get that the gain is more than 1. Therefore, we reduce the gain. It is difficult to observe. We want to know the frequency values. Hence, we add the frequency measurement. The oscilloscope only shows the frequency of the signal that appears on the screen. Therefore, we necessary to move the signal in the horizontal position. For this position, the frequency is 101 kHz. Then we move it, the frequency decrease to 99 kHz. It is observed that if the amplitude of the message signal increase, the frequency of the output signal decrease. We would like to emphasize that we must zoom in on the signal and move the horizontal position to observe the frequency. Okay, let's go to experiment 2. This experiment is very easy. From the previous experiment, zoom out the signals. You remember FM or frequency modulation means that the frequency of the carrier signal change according to the message signal. Its amplitude and phase are constant. Focus on the oscilloscope. You will see that the amplitude is not constant. This change is a type of distortion. In fact, the amplitude must not vary. Therefore, this change is the drawback of narrowband FM. The gain can be reduced, but the distortion remains. Yeah, finish experiment 2. Okay, let's start experiment 3. For generating the sinusoidal signal that change according to the message, we can use the VCO to generate that signal. That means the VCO can generate the FM signal called wideband FM. Therefore, we use only the VCO module for the experiment. We get that you can use it very well. Okay, we put the VCO module in the immunogenes. Firstly, we connect the message signal to the input of the VCO and show it on the oscilloscope. We will see the sinusoidal that have a frequency of 2 kHz. Then we display the output of the VCO on the oscilloscope. We will see the signal like this. Let us decrease the frequency. We press the run on stop button and move the signal to zero. Observe. If the amplitude of the message signal decreases, the frequency of the carrier increases. In contrast, if the amplitude increases, the frequency decreases. Next, we increase the frequency. It tends to be the same. This signal is called a wideband FM signal. Press run or stop. It is found that the top end of the FM signal is contact. That means the frequency is without distortion caused by amplitude variation. This is the difference between wideband and narrowband. Okay, and experiment 3. Into experiment 4. This experiment is a simulation of the wideband FM signal detection. For FM signal, the message signal is embedded in the frequency. The manners of message signal in the low frequency and the high frequency are different. Therefore, it is called zero crossing detector. This is the transmitter side. For generating a zero crossing detector, we necessary to use 3 modules. Firstly, we will use the comparator. The comparator is in the utility module. This is the receiver. Next, we put the twin pulse generator in the immunogenes. We also plug in the low-pass filter. FM signals are more robust to noise than AM signal because the frequency is more difficult to vary than amplitude. This is wideband FM signal without external noise. Connect it to the input of the comparator. Next, we use the ground as reference signal. Then we display the output of the VCO and the output of the comparator on the oscilloscope. It can be seen that the output of the comparator only appears in the positive region. Next, we will show the varied frequency range. There is a high frequency range. That range have many rectangular signals. The range of broad frequency have a small number of rectangular signals. We must use the run-on stop button to observe the signals. The comparator is a rectangular generator. The rectangular signal only appears in the positive regions because we use the ground as reference. After that, we connect the output of the comparator to the input of the twin pulse generator. Then we show the input signal on the oscilloscope. Next, we also the output of the twin pulse generator. It observed that the output signal is narrow. It is similar to the number counter. It indicates the number of zero intersections. The blue wave is like a decreased signal. Next, we connect this output to the input of the low-pass filter. The output of the low-pass filter must be the estimate message. Okay, we link the message to the oscilloscope. Then we show the output of the low-pass filter on the oscilloscope. We reduce the cut-off frequency. Therefore, we can demodulate the wideband FM signal by zero-crossing detector. Next, we will use the noise generator. We put the noise generator in the immunotherms. This is the transmitted signal. Next, we use the adder module. We connect the transmitted signal to the input of the adder. Then we connect the noise signal to the input of the adder. The gains must be 1. Next, we connect the output of the adder to the input of the comparator. Adjust noise power as 0 dB. We adjust the gain to be low. When we increase the power of noise, the signal is still robust. Do you remember for AM signal, we use the amplifier to increase the power of noise. Then it results in the signal. We are not sure, it may be some restrictions. Okay, next experiment. We show the FM signal on the oscilloscope. Reduce the frequency. We add the frequency measurement. We expand the signal and observe the frequency. We adjust the frequency to 130 kHz. When we move the signal, the frequency varies. Then we will observe the signal in the frequency domain. We set the stop to 200 kHz. Generally, FM signals have infinity bandwidth, but the bandwidth of wideband FM is calculated by KHON rules. Adjust the start to 1 kHz. And adjust the reference level. We try to set the stop to 300 kHz and 400 kHz. Then adjust the reference level. Please remember this figure. We will switch to the narrowband. The narrowband must have lower bandwidth. Therefore, we contract the narrowband FM again. We put the phase shifter in the emulations. Then we also put the multiplier, also put the adder. We connect the master signal to the input of the phase shifter. Next, we show the output of the phase shifter and the message on the oscilloscope. We connect the output of the phase shifter to the input of the amplifier. Then we show the output of the amplifier on the oscilloscope. Next, we connect this signal to the input of the multiplier. We multiply it by the carrier signal, that is the sine wave. After that, the output of the multiplier is connected to the adder. Then we connect another carrier signal to the input of the adder. Next, we show the output of the adder on the oscilloscope. Reduce the gain of the adder. Okay, this is the narrowband FM signal. After that, we will observe this signal in the frequency domain. Focus on the sprite program. We change the stop to 600 kHz. Next, we adjust it to 1 MHz to vary the reference level. Then we also compare it with the wideband signal. Okay, this is the wideband signal. Then we adjust the reference level to observe the signal. Okay, this is wideband signal. Change to narrowband FM signal. It is found that the bandwidth of the signal is lower. The right position of the signal appears at a frequency of 200 kHz. Okay, switch to wideband FM. It is observed that the bandwidth is wider than the bandwidth of the narrowband. Yeah, finish experiment.